Okay. Okay. Hello, everyone. First time I have to use the microphone this way. So welcome. I guess I won't make any introduction this time, unless there's any question, urgent question about exam exercises, anything. Perfect. So let's welcome our first speaker, which is Federico Trivias, and he will tell you a bit about what he works on.
Thank you, Simo. Okay, it works. I feel more comfortable with this. I can place it somewhere here and it's gonna be fine. So thanks everyone for being here. I know it's late. I know you have to study for your exams. So I'm really happy that you still managed to be here and you're curious about something, and maybe you can also learn something today. Do language models dream of electric clocks? Very big question. Today we're going to talk about interpretability. How many of you know what interpretability is? Nobody. Some of you. Okay. So I'm going to present a little bit what the topic is about, and I'm also going to present some of my findings. And by the end, maybe you'll be convinced in like taking a PhD in interpretability and help me out with my work. Okay, who am I? I am, as I was introduced, I'm Federico Tibias, PhD at UKP Lab. I'm interested in like this thing called interpretability, temporal reasoning. So that means reasoning about like things that happen at some point in time, and also quantum NLP, which is some sci-fi stuff, which we don't need to be concerned about today. Anyhow, the talk today is about interpretability and then mainly about my work and findings. So first thing first, what is this interpretability thing? So we know how language models work in the sense that we know how like the blocks are defined, we know what mention is, we know what like embedding and so on are, but how do they really work? Like we have in place like this whole next token prediction training, and that gives us some specific weights and 70 billion of them. And they manage all together to have very complex functions. Like they remember crazy things about the past. They can reason about pretty much everything. So what is the mechanism that actually allows them to do this? So interpretability tries to explain how they work. And this is somewhat different from explainability, which you might also have heard about. Explainability is kind of like a broader branch of NLP, which is about why essentially the model answered in a specific way. We are more interested in the how specifically, so in the technical details, and like what are the inner mechanisms of this AI things. So I wanted to present to you a bunch of techniques, like really broadly sketched out techniques of how interpretability is done in the present day, and then present my own findings. So first idea is the concept of probing. So have you heard, like as you know, like these language models have this kind of embedding space, like these hidden states which contain all the information about text that the model has read so far. So probes are essentially trying to find meaningful directions in this space. So for example, what happens, imagine that you have 1,000 recordings of these hidden states when you have like passed your model, when you have like let your model read a bunch of text. And now you want to ask the question, well, can I distinguish, for example, truthful sentences from deceitful ones? So some very abstract and complex, how can I say, partition between two concepts. Turns out that you can. So essentially what you do is you do a linear regression. It only takes a linear regression in the hidden states of a model to identify a direction. Like imagine it as a bar. You can just control it, like place the embeddings more to the right. The model becomes more truthful, says sentences that are factually true. You turn it more to the left, and the model becomes more deceitful. It starts lying to you. And like this is a general technique that has been used in the past for finding things such as deceitfulness, such as the political leaning. Like you can get your model to talk more about politics in a left-leaning or right-leaning way, simply by training a linear regression on your probe, like finding a line in your hidden states, and then shifting more to the left or to the right your embeddings. Kind of fuzzy so far. If you have any questions, just raise your hand. I'm happy to answer. Okay, everybody's either confused or has no questions, so I take it as a good sign, I guess, and I just go on. Another technique is called lensing, logic lensing. So essentially, you know that like these models process the input across many layers, and by the end you have some logic, so some representation of the whole sentence. And at the final step, you decode it back into the real dictionary of your like human readable dictionary. So what happens instead if you decode the inner layer of the network? So instead of just decoding, I don't know, we have here the example sentence, the best country is, of course, the model will say Italy. So instead of saying this, what if we try and decode some layers halfway through the network? Well, maybe we can find some surprising behaviors. So for example, in this case, we decode in the middle and it says France. I don't know one here is French. Is there any French here? Okay. The idea is that by doing this, people have found, for example, that this is kind of a bad view. It's very small to read. But the idea is that across the layers of a network, representation, so what the model is thinking about, is kind of continuous. Sorry, it's passing continuously from the input to the output, in a way that you can trace. So internally, the model are thinking more or less in the same language as we humans are. They're not speaking an entirely different language, and you can decode at any point in the computation and still get some meaningful response. So far, so good, I hope. Another technique that has been used is causal tracing. So this is like a broad range of techniques. This is more like a field of interpretability. And the idea is, okay, we want to find how models work. What about we try and break it down? We break selectively some components of the model and see if the model becomes more stupid. So, for example, we have some behavior. We know that the model can do sentiment analysis very well. Let's say that we zap one layer of the network, or we destroy, like, okay, we zero out or we add noise to some attention heads of the model. If the model stops working, then we can tell that that attention head was important, right? If it stops answering well. So the ultimate idea is to essentially, you have your whole model, you have your whole set of operations that the model perform, and you just like zero out, remove one by one these operations until the model breaks. Doing this, you can essentially recover a circuit. So a minimal set of components that are useful for the model to solve a specific task. And this is, I guess, useful because you can kind of see internally which algorithm the model uses to arrive at a certain answer. So for example, here, capital of the state in Dallas is, and you can see this whole trace of behaviors, and the model comes out with Austin as the answer. So something, something more specific that's more related to my topic is residual stream analysis. Do you remember what a residual stream is? Simone, you don't teach them anything. What do you want to see? Okay. Anyhow, it's fine. It's the idea of a residual stream means the hidden state of the model. So we're always talking about the same thing. It's just a different way of saying the same things. So the idea is, okay, we have looked at the components, we have looked at like weird directions. What if we try to study the hidden space as a whole? Like, what does hidden states in the model represent globally? There are like some ways of exploring the hidden space and understanding, like, I don't know, in this portion of space, they represent this thing, in this other portion, they represent this other thing. And like, there's a few techniques to do this. First one we've already discussed, is probing. So you know that like this direction tells that you can find more truthful sentences. In this other direction, you can find more deceitful ones. But there is others. There is so-called sparse autoencoders. So how many of you have heard of encoders? Like, sorry, autoencoders. Some people, not all of them. But okay, the idea of sparse autoencoders, while as you know, like encoders essentially take some, vector, transform it down to a lower dimensional representation, and then bump it back to the original dimension. Here we do the opposite. So we take a hidden state from a model, we bump it up into a dimension, like into a vector, which contains, I don't know, 100,000, 200,000 dimensions, and so becomes very much more sparse than it was before. And then we turn it back into the original representation. Why? Why do we do this? Because when we are in this like kind of extended space with like 200,000 dimensions, we hope to see that single features inside of the model will light up. So, for example, let's say that we mention cat or dog or turtle. These things will map to a specific, value inside of this vector. So the whole vector will be 0, except for like 1 or 2 of these like cells, which will fire up to 1. And by doing this, we can essentially recover what are the latent concepts that the model is thinking about on a more like fundamental way. Like what are bigger concepts composed of like lower level things. Finally, one other method that people have used to explore this space is just like classic dimensional interaction. How many of you have used PCA, principal component analysis? Again, not everyone, but some of you have. So there's very classical machine learning things that you can use to essentially reduce your dimensionality from 700, 3000 of the hidden space to just 2 or 3 and find maybe interesting relationships, which is a spoiler what we're going to do in the second part of my slides. So I wanted to talk to you about the linear representation hypothesis. Scary words. So the idea is, if you look closely at how LLMs represent concepts in their like hidden states, they don't place them randomly. If you think about the presence of a concept in a sentence, so I don't know, I just mentioned the word dog in my sentence. The presence of a concept in a sentence will be encoded always along a certain range, certain direction into the latent space. So all the sentences that mention dogs, for example, will have some component will lie somewhere on a line, right? Which refers to the concept of dog. Like the presence of the concept of dog in my sentence will make a concept lie along a specific direction. And the more the concept is present in the direction, if it makes sense, the further ahead in this line, the representation falls. So by doing this, we can study how representation behave in a more like in relationship to each other. So, for example, how do the representations of months lie in the embedding space? Are they just scattered at random, or do they follow some patterns? We discovered that it's the second hypothesis. So, if you look at, for example, sentences containing months or containing years of the 20th century, you find that they form organized structures in the embedding space of models. So if you take, and by the way, when I talk about the meaning of a sentence, I mean, imagine like you take an embedding of a sentence and you try to plot it out. Well, again, like it will not follow randomly, it will fall according to a specific pattern. And these patterns are, as like previous literature finds, more or less ordered in space. So, for example, years of the 20th century kind of follow this like U shape, this V shape across space. Again, months of the year follow some circles, and in general, they land on some so-called manifolds. How many of you know of the word manifold? Some brave mathematician people. Okay. Basic concept of a manifold is, imagine you have a sheet of paper. How many degrees of freedom do you have to locate a point on this sheet of paper? Any guesses? 2. Perfect. Okay, now imagine you crumple this sheet of paper, right? And you still want to locate a point on it. How many degrees of freedom do you have now? 3, yes. But if you know that the point is on the sheet of paper, you only need 2. So essentially, you have a low dimensional surface shape embedded into a higher dimensional space. So only to locate a position, if you know the hypothesis that this position is going to be somewhere on this sheet of paper, you can reduce the number of degrees of freedom to a lower number and just locate a point there. Models do this implicitly. So they organize the information, not completely at random, but over some low dimensional structures in the latent space. So that means that everything you need to characterize, for example, the time of your sentence, whatever, will be encoded in a much more dimensional space than 784, whatever BERT needs, for example. So far, so good. Any questions? Really, like just ask around if you're curious about something. Yes?
Are there some like patterns when certain, patterns arise? The U shape in the years of 20th century and the months of the year surely have different patterns. But are there some like rules to this, or is it just depending on the PCA how you reduce it?
Thank you for this question. Yeah.
Please repeat the question because otherwise it won't be audible in the recording.
Oh, yeah, sorry. So the question from the classroom was, are there any patterns to how different features are represented? Like some of them we see as circles, some of them we see as V, U shapes, but like, are there some rules underlining which shape they follow? Yeah. And I'm glad you asked this question. This is actually the whole meaning, or like the whole point of the paper. So there is a lot of meaning. So for example, people have located coordinates in space. Like they have prompted the model with a bunch of location in like the real world. Like I don't know, they mention Burj Khalifa, or they mention Empire State Building, like locations in real life. And they can find a three-dimensional space in the embedding space of the model that more or less matches where the point is in real life. And as you can see, there is a one-to-one, almost one-to-one correspondence between like where the point is and like a real map of the world. So it's essentially as if models inherently can place on a mental manner kind of where things are according to some order. So in this case, people have found like a dimension, like a plane corresponding to locations on the planet. These other guys have found directions in the embedding space, which correlate to, for example, the birth year or death year of some people, or the population or elevation of some cities, whatever. But like the point is that these structures are ordered; they are not scattered randomly, and they follow some distinctive patterns. But the question, okay, wait, maybe I have one more slide. Okay, yeah. The question still remains, like, again, why do they follow that specific shape? Why was the planet encoded as a geographical map instead of some other, I don't know, torus shape or some Mobius strip or whatever? What do they look like? Like if you take an arbitrary feature, an arbitrary numerical property, an arbitrary concept, what will a lot of these concepts look like in the embedding space? Are they actually used by the model? Like, do they order them just because, or there's actually some usefulness behind it? So, and of course, like, how can we discover them? How can we detect them? So what we have, and like these slides look terrible. I don't know, like the conversion messed something up, but it's fine. So how can we explain this? And in like very simple terms, like how do LLMs organize their thoughts? Is there some order there? And how can we actually reinterpret these thoughts? How can we read their minds? Well, the answer is a method that we, okay, all right, sorry, before I get to that, we have, okay, the specifics of our experiment is that we have been focusing on temporal reasoning. So what if we ask the model a lot of questions about, I don't know, this guy was born on this date, this guy was born on the other date, was born first. Or another type of temporal question is, I'm going on holiday for 2 months and I'm going on holiday for 3 weeks. Who comes back first, right? So there's a lot of questions you can ask about temporal reasoning that the model will, how can I say, reshape in different ways to answer your question, essentially. You see that like these are slightly different kinds of reasoning. Like duration needs you to think about like a start point and an end point of an interval of time. Something else like we have an experiment about actions taken at specific times in a day. Like, I don't know, I go to bed at 23:30. This guy goes to bed at 3 a.m. in the night. Who goes to bed first? And here you need to have a notion of circles, right? Because the day looks back. So we assume that different types of reasoning will have different shapes. But what are these shapes? So what we do, okay, this is the data set I was just saying before. We have a couple of different features that you can represent in your model. Okay, this is like more technical details. The idea is that we just cut the model up in some specific location and then look at the embeddings, but it's not super important. The idea is that when you try using existing techniques, like maybe you have heard of them, there is PCA, there is LDA, PLS is a bit less known, but the idea is that they all perform dimensionality reduction. So they go from 700 whatever dimensions to 2, 3 of them, and you hope to be able to interpret them. Well, all of these methods have failures. They break down at some point. Because, for example, PLS is essentially a linear regression, can only find linear shapes. So it expects these structures to be lines. LDA expects the features to be clusters, expects them to be classes, but there's no notion of order. And PCA is just doing its best. Poor thing, it's not finding anything useful because as like PCA just looks into the direction of maximum variance. So they're not necessarily encoding any of your features. So the idea is that existing techniques don't cut it. We need something that is supervised because we have some labels that can use. We want something that finds more than just lines because our features are very complex, can be very complex. And finally, we want to enforce order in the points. So LDA just doesn't cut it because of this order thinking. So what we come up with is this supervised multidimensional scaling, which, okay, I'm not going to bore you with the details. It's just dimensionality reduction technique, which has some notion of order in between. Then if you're curious, you can raise your hand and ask questions. The cool part here is that it's in closed form solution, so it's very easy to run. Thanks to this, we are able to have a lot of very cool findings. So first you asked why do they have a specific shape? Well, what we find is that we throw these experiments at different models, and we find that across different model families, so one model trained by Google, one model trained by Meta, one model trained by some guys in China, doesn't matter. They all encode knowledge, the same features in the same way. So they always follow, as you can see in this like plot to the right, the same kind of patterns, no matter which model it is. Second point, there are some preferential patterns. So we have a way of essentially quantifying how good of a fit a certain structure is, be it a line or be it a circle. And we find that consistently, some problems are better encoded by certain structures. So for example, dates of the year are primarily encoded as circles across all of the models we have looked at, be it like 3 billion, 8 billion, 70 billion, be it when, be it anything. And here you can find like the electric clock as was promised. So hours of the day are encoded in a very circular pattern, which is very easy to read. So you can see here midnight is here, you can see here hour 20, 17:30, and then it loops back kind of to midnight again. And this is not random, and we find this consistent pattern everywhere. Any questions on this? Yes.
So we're talking about orders. What are orders?
Yes. So the question was, what is an order? How is an order defined? So it's essentially defined, depends on which feature you are looking at. For things like this is like there's only one monodimensional ordering you can really do on hours of the day or days of the year, right? For more complex things, I don't have an example, unfortunately, but for example, for imaging coordinates on the planet, you can, and I asked you, which these 2 points are close or not? It kind of depends if you're talking in like 3D coordinates on a globe or 2D coordinates on latitude and longitude, right? So there is no, ultimate better solution to this. You have some information, and what we wanted to do is essentially to find what the model thinks is the best ordering. So another example that has been done in other literature is RGB colors, like colors in general. As you know, there's multiple ways you can encode colors. RGB, HLS, whatever. There's many coordinates you can use. Models use HSL, for example, instead of RGB. Instead of like having a 3D space, they use this kind of ring structure again to encode the shapes. So it's up to the model, essentially. But it kind of matches what we expect to find also, which is the interesting part. Any other questions? Okay, you seem convinced. So more findings is that these feature manifolds, this is how they are called, depend on the task. So let's say that you encode the same information. So Alice was born on the 16th of May, Bob was born on another day, Charles, blah, blah, blah. And then you ask different questions. If you ask the oldest is dot, 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 and you expect the model to generate the correct answer, well, what you're going to find is a circle. If instead you ask the only one born in summer/winter/autumn, you're going to find a totally different pattern. So as you can see here, the pattern is going to be a circle. So, and again, if you ask who is the only one born in a cold month, you're going to find different clusters. So even though the initial information was the same, the question you asked totally reshapes the structure of the manifold you actually discover. And like full disclosure, the clusters are not really manifolds, mathematically speaking, but yeah, it's good enough. The structures change, essentially. That's the takeaway. One other cool finding is that, okay, we wanted to ask, okay, are these structures actually good for reasoning? Like, are they used in reasoning at all? And it turns out they are. So if we try to add noise to this like low dimensional structure and then kind of plug it back into the model becomes like goes crazy and like the accuracy drops by a lot, essentially. So we know that these things are important. And you can also see by the way the manifold is scattered. Do I still have time? Maybe 2-3 minutes. Okay, then maybe I jump to the conclusions. And by the way, final point is that models are terrible at temporal reasoning. Like we have like looked even at Llama 70 billion and they are quite bad at a lot of things. So yeah, very last point is that a lot of these structures essentially are found also in the human brain, or like looking at rats. We also find similar like neural manifolds, it was covered in the slides, but also looks like the brain is encoding information in a much structured pattern with fewer degrees of freedom than it has access to, for example. So I think this is very interesting. And it has very deep connections with how we as humans think. And hopefully I can use it to make more papers and like actually do some real applications out of this. With this, I would like to finish and thank you all. If you like this, if you liked how I talk, I mean, you have terrible taste, first of all. But second thing, I also have a course in the winter semester where we do projects on software engineering connected to NLP. I also say a few things about software engineering, blah, blah, blah. So come check it out. It's a great course. I'm biased. Yeah, I know. But I'm also looking for thesis students. So if you're looking for a thesis in the winter semester, just reach out. This is my contact. Do I have time for questions?
That's why I got some questions.
Okay. Any questions? Okay, let's go here.
How could these patterns help us to improve LLMs? Like, how can we use it as a benchmark or something?
Yeah, so the question was, how can we use these patterns to improve LLMs? So something we have found is that the better the model performs, the better its structure is. So the fuzziness of a circle like will be less if the model is it's better performing, essentially. That means that the better the structure, if we can build models with better structures, they will also perform better. So maybe during training, we can kind of detect this structure when they arise, and we can have some loss that kind of enforces a specific structure on the model. And this will help in a couple of like very specific domains, for example. The open question is, can we find more general patterns in broad reasoning, for example? Yeah. Was it on there? Yeah.
So similar to this question, you mentioned that if you add noise, model goes reserve. So what if you remove noise? Does it make the model better? Also, can we use it for data science? Because we can find similar.
So data generation would be my follow-up. So actually what happens if you forcefully move your position on the manifold on another point? Like if before the model was generating April, will it generate October, for example? I think so. I have not tried yet, but I have very good evidence to believe they do. And the original question was, how do you remove noise? I mean, it's kind of like tricky to define what noise is. Like what you could do is essentially to collapse a point on the closest point of the manifold. This I haven't tried. Maybe it would work. I think it's a good experiment to look at, actually. I don't know. I think maybe somehow would improve something. But also like a lot of noise in models is actually important information that you just don't know about. So it's kind of tricky detecting what good noise is versus what bad noise is.
Maybe a master thesis.
Maybe, yeah, perfect. Anybody wants? Answer that question? Yeah. One, I think we have time. I don't know. You tell me. Okay, I can go.
I think my question has resolved itself, but I thought maybe it's possible, like we saw the circle with, or you mentioned that if the data more resembles a circle, it's usually better, right? Like if it more resembles like the clear structure of the circle. And I thought maybe you can just, well, force the data into the circle, but I mean, you said it wasn't a smart idea.
No. I mean, I think it's smart. There is an issue, however, with this reasoning, is that, so if you look at this plot again that I have here, sorry, yeah. The question was whether enforcing a determinate structure on some data. So if, there is noise, but what if we get rid of the noise and we instead force a point to be on a circle? Will the model perform better? And I feel like not necessarily so. Like I could try, but it's not necessarily so. Because as you can see, there is like these bars on the right are like the scores of different shapes. What we found was that models will fit many different shapes at once. So there is a preferential one, there is preferentially circle, but there is also preferentially a line. So what does it mean? It means essentially that models encode the same information in multiple ways at once. So if you look at it from a perspective, imagine a helix in space. If you look at it from above, a helix is a circle. If you look at it from the side, a helix is also a kind of line, right? So, I mean, maybe it's better. You can see it better in one of the previous slides. Look at PLS. That's not a line, that's a spiral, clearly. It encodes both properties of a line and properties of a circle. So is there a true way model encode things? There is a preferential one, but it's not the only one. So if you enforce points to land on a circle, you're getting rid of a lot of other information. So that's not necessarily better. I'm getting signals to stop talking. So I thank you all again. I hope you learned something new. I hope you will reach out and ask for a thesis and you will come to my course. Okay, thanks a lot.
Thank you. So yeah, this was the first talk. By the way, I cannot talk for everyone, but I think some of the speakers will be able to stay a bit after the lecture. So if someone is curious or someone has, oh, I try to do this and it's related, blah, blah, just reach out. With this, I think we can move to the next speaker, Ammo. So we're moving to security in LLMs now. Do you want to time? I will time you, but okay. Do you want to decide? You all people did like Britney Spears, you decide.
Hello. Is this good? Okay, cool. Okay, so I'm also a PhD student in the same lab as Federico. I'm a second year PhD. My topic is mostly revolving around security, privacy of large language models. And with this talk, I just want to talk and brainstorm about the current issues and emerging issues as we start to use larger and larger models. And you'll discover that there are a lot of issues that even though you can get good performance with these language models, and of course, I believe in this course, you learn how to train good models. But what I want to get out of this talk for you guys at least is to see that just doing a good training, achieving good accuracy is not enough. There are a bunch of auxiliary things that you need to care about in any deep learning task. So as we all know, mostly after 2023, we have seen an exponential growth in the uses of LLMs. I'm sure all of you guys also use ChatGPT daily. It was like fastest app or website to gather millions of users, and it can solve pretty much most of the easy tasks that at least classic NLP tried to do for the last 10, 20 years. Text generation, classification, knowledge answering, all those. Now you can just prompt ChatGPT, open it on your phone, open it on your laptop, and you can solve it pretty easily. This is a tweet from like 2 or 3 days back, where not just on general purpose tasks, models are now becoming even supposedly smarter than humans, where ChatGPT reasoning was achieved the International Mathematics Olympiad gold medal, which is apparently quite a strong display of LLM reasoning performance. So what is the secret sauce here, right? We know in this course, you've seen how to train good models. I'm sure you must have guessed as you increase the scale of the models that you train, as you increase the number of trainable parameters, and this is the state of the art in each year in NLP. Google released BERT back in 2018. I'm sure you've looked at encoder transformer layers in the course and so on. And then we started moving to decoder only models and encoder, decoder, T5 models. And so the takeaway here is the more parameters, the more trainable parameters that you add to the model, the training is more successful. The other side of the coin is more data. So if you have high quality, more data, more training tokens, the model seems to perform really, really well, which is, so GPT-4 is supposedly trained on 13 trillion tokens or words, which if you quantify it in like normal human terms, it's like 650 kilometers of shelf lines in a library, in the TUDE library and so on. And of course, parameters and model sizes, what we've already discussed. However, despite this apparent success of large language models, what we see or what we observe is there's a huge catch here, which I teased initially. That is, models are much more prone to leak their training data sets. So this is a very popular paper from Nicholas Carlini from Google DeepMind, where they prompted ChatGPT 3.5 2 years back, and they came up with some adversarial prompts where if you just prompt the model with some poem, the model starts, because the model has no hidden dimension of where to go next in predicting the next token, it just falls back to revealing its training data, which is these, and this is actually a real world private data set. And the other example, real world example I wanted to talk about is, I'm sure all of you code, you use VS Code, you use GitHub Copilot, and some of you now recently use Cursor. So you have this autocomplete suggestion thing, right? And some people found that if you cleverly use this autocomplete tag suggestion, you can actually trace back some of the training data that this Copilot model was trained on. So this is a real world example, happened with me as well. If you hit tab after saying some very common strings, it can actually reveal GitHub links, private website, private addresses, and so on. So this is essentially the problem I want to talk about in this talk. Of course, we are scaling up huge number of models, huge number of parameters, huge number of training data, but there is a huge problem of privacy and security, which most people generally overlook while looking at these models. And this is what I want to talk about. So let's start with privacy issues in LLMs. I would like to give like a very high level, broad overview in this talk. We'll discuss two specific types of privacy issues. The first is data leakage, where we've already seen real world examples where the ability of an adversary or a hacker, the hacker essentially wants to infer some properties about the data that the model has been trained on, right? So this is something that at least classic non-NLP people are really careful about. For example, if you're doing a clinical trial and you train on real world patients' data sets and you do some bunch of analysis, you do some exploratory data analysis, all that, and you want to infer a very general statistic, smoking can cause cancer. This is an average statistic, which is okay. This is not private or personally identifiable information. However, these models also enable you to talk about specific users, and they can leak data about a specific person or a patient. And you can essentially infer that Alice has cancer just based on the trained model parameters. How do people do this is something called a membership inference attack, where it's a generalization or a simplification of the training data leakage, where the goal of the adversary is to use a target sample and look at the model parameters and just know whether this has been used to train the model or not train the model. Right, and people have shown that this is, I think, from BERT and GPT-2. If you just plot out the perplexity or loss that the model assigns to any input string, there is a very clear distinction in terms of what the model has seen in the training data and what the model has not seen in the training data. So the general intuition here is the model would assign lower loss, cross entropy loss, which I'm sure you've heard about in this course, lower cross entropy loss for the samples that it has already seen and larger loss for the samples that it has not seen. And this becomes sort of your baseline or a very vanilla rule to infer whether a text string has been used to train the model on. Then people have come up with more sophisticated attacks. This is a neighborhood-based attack where, let's say, you want to check whether this target sequence X has been used to train a BERT model. What people do is they make multiple copies of this sentence and they randomly replace some words in the text of this prompt and they send it to the model. They get the loss of all of these and then they come up with this threshold, and if it exceeds or doesn't exceed a threshold, they classify it as a member or a non-member. So these are sort of the real world implications of these language models that we've learned to train in this course. And the other attack I want to talk about from the privacy perspective is model inversion attacks, which again connects to what we already discussed, training data leakage. This is a more sophisticated form. You are not just checking a binary 0 or 1, whether this data set was used or not. You are actually trying to reconstruct the exact text tokens that the model has memorized. And people have shown existing research. There's a huge, these are all the categories that you can essentially extract from a GPT-2 model without ever looking at its training text data, just based on model access. If you download your GPT-2 from Hugging Face, you can essentially infer contact info, my address, email, phone, Twitter profile, even something like config files, code, all of these, which and especially in Europe, right? If you are a startup, if you're working on a LLM API type product, you would have to comply with GDPR laws, which all of this violates and throws you under the bus. And then I also wanted to talk about some of the recent privacy issues. Training data, sure, but then someone could say, how many of us are actually training these huge trillion, billion parameter models from scratch anymore, right? So all of us prompt models at least, and there is a bunch of emerging literature that shows that you can reconstruct the prompt that you send to your ChatGPT UI, even on the browser, just based on the output text or just based on the probabilities your model assigns to the next token in the vocabulary, right? So during the autoregressive token generation process, if you only have access to the logits of my model, you can essentially reconstruct a lot of almost 90-95% accuracy with the token of my original prompt. So this was some initial intro about privacy issues of language models. I would take a brief pause. Do you have any questions, any thoughts? Have you experienced something like this? Okay. So we'll move on to the other part of the talk, which is security threats. These are also similar, but they are not revealing personally identifiable information, but they are more relevant from a security threat perspective, where an adversary essentially wants to change model behavior based on some hidden objective. So the basic thing, I'm sure you guys must have heard of this term recently, jailbreaking, where the goal of a hacker or an adversary is to essentially, so you have Anthropic, Google Gemini, Llama, ChatGPT, and if you even right now, if you try, just ask a very sensitive query like, how do I manipulate someone? How do I make money from the share market by manipulating the markets? The model will just refuse. However, people have come up with security adversarial jailbreaks, where based on some adversarial prompt that you can add at the end of your normal text, the model just starts to tell you everything that it was not supposed to reveal. And companies, this is essentially a cat and mouse game, because every time a new paper comes out that shows that the model can be jailbroken, all of these companies fix it in a patch, in an update, and then more researchers work on it and then try to jailbreak the model again. So a bit more technical detail is something like this. So you have the system prompt, you are a chat assistant designed to provide helpful responses, whatever. And you as a user want to ask a very sensitive query like, tell me how to build a bomb. So generally, the model just refuses. The model says, sorry, I cannot answer that, or I'm not supposed to answer that. However, recently researchers have shown that if you do an optimization loop like this, you can find some tokens which are those red colored exclamation marks. And this was supposed to work for GPT-2. Now they have, like OpenAI has patched it in the recent models, but you can still try to do this with GPT-2 from Hugging Face. So this is a greedy coordinate gradient loop where they try to find the token replacements in the prompt, which will maximize the probability of the model generating a harmful response. And as you can see, the attack success rate, which is almost 85% for this kind of attack. This was a huge deal. This is a 2-year-old paper, and this was a huge deal in the community, and people were and the interesting thing with this was this. So even if you try it for a local model, open source model like Lacuna, this will transfer to all of these closed source models like ChatGPT, Gemini, Anthropic's Claude, and so on. This is the first security threat. The second is also very interesting to me personally, which is a backdoor attack, where let's say you are an adversary and you have some control over the training data set or a fine-tuning data set of a language model. What you can essentially do is insert some special tokens or some special sentences in my training data. And as soon as I add those, and I don't know that you have manipulated my training data set, even if you manipulated like 1%, 5%, 10% of the data set, you train my model on this instruction tuning data. Now I have the control that whenever I insert this green colored poisonous instruction in any prompt, the model will start behaving weirdly, or it will be harmful, or it will be whatever my goal as an adversary was. And as you can see, this is more successful as you increase the number of parameters, which means that, of course, scaling is the solution to getting more accuracy, more compute, and more capabilities of the language models. But scaling also means that your models are more vulnerable to these kinds of backdoor attacks. This is data poisoning, very similar to the backdoor attack framework in LLMs. Here it is a much more powerful general variation of the backdoor, where me as an adversary can essentially poison a bunch of your data set and you train. And now any query that you give to the model just is super harmful. It is always not answering, not helpful, and all that, right? So for example, this is from a recent Nature paper where they show that even if I manipulate 1% of the training data set and you fine-tune your language model on that, the harmfulness of 0.1% poisoning is like plus 20%. So even if you can manipulate just 0.1% of training data samples, the model is super harmful for 4 billion parameter size. And these are some real world examples. I've only poisoned 0.1% and the model is now unaligned, and it is saying COVID-19 vaccine is not effective. It is saying antidepressants do not work, and so on. It has essentially, we've jailbroken the model by just changing 0.1% of the training data set. So these were the two sort of facets of security and privacy issues in language model that we face right now. And now I'll quickly discuss some of the solutions that we as a research community have come up with. There are 4 broad areas that you can essentially use to safeguard your models. I'll start with differential privacy, which is sort of the gold standard if you talk to any security researcher, even at TU Darmstadt. The goal here is you add carefully calibrated noise, similar to some of the previous discussions we've had, either at the model layer, embedding, token level, whatever. And the amount of noise you add guarantees that the amount of data that you can leak is not above a certain threshold. So the intuition is essentially this: you have a database and you want to protect Joey's data, right? And I train a model M it gives me an answer A. I train another model M on just removing Joey's data, and I get an answer B. So the goal of differential privacy is it should be indistinguishable in general, but I cannot infer anything private about Joey's data. So in theory, differential privacy gives me guarantees that no adversary can conduct a membership inference attack on a language model as long as I add enough noise. And this noise you can sample from a Gaussian distribution. They assume some mean and variance and sample from that Gaussian distribution. So we recently had a paper on LLM alignment data. A bunch of work has already been done on this, where you do differential privacy at different stages of a model pipeline. So for example, you can do it at pre-training, you can do it at fine-tuning, you can even do it at in-context learning. We do it during the alignment process. And we come up with this membership inference attack first to show that this is a real world sort of a privacy issue. And what we do is very simple. We essentially add some noise vector at some layer L of the language model. Right? That's all you need to do. And it gives you theoretical guarantees on the amount of data that the model can leak or cannot leak. Some more results. We benchmark it across 4 model families and different kinds of behaviors: hallucination, refusal, sycophancy, and so on. So the model accuracy is preserved. It's even better than zero shot. But because generally, as soon as you add noise, the model starts misbehaving, right? The model maybe starts generating gibberish outputs. That is why we carefully calibrate the amount of noise that you add to the model. And it is supposed to work well within some range of 0.02 variance. The other solution that you can, if you don't want to go the theoretical route, is something called red teaming, where you intentionally simulate an adversarial attack on your language model, and you sort of do a loop, iterative loop kind of development where you simulate an adversarial attack. Okay, now you see that, okay, my model is vulnerable in these categories. You evaluate it, and then you do the full training pipeline again. But this is generally costly. However, companies at the scale of, like, this is a recent Gemini AI report where they released a 60-page handbook on how to red team your language model. So if you guys are interested, you can take a look there. The third kind of defense against these privacy security issues is something called guardrails, which is, if you really think about it, it's very intuitive and simple, where the goal is you just have some small models or small classifiers that can infer whether my prompt contains something sensitive, whether my prompt contains something harmful, which all of the research community suspects that ChatGPT, all these black box LLM API providers already do. Because if you ask ChatGPT right now on your phone something harmful, it will very quickly just refuse to answer. It is not even sending the data to the ChatGPT server, because they have these smaller input guardrail models which classify, okay, this is a harmful request, I should not even answer this, and the model refuses. Finally, there's a super interesting and emerging area of research called unlearning, where sure, you train your model, but how much guardrail or differential privacy can really help you? So what people have tried to do is just assume that you trained your model on some poison data, harmful data, recon data. What can you really do now? Or the other perspective, the user-centric perspective is, if you train a model on, let's say, TU Darmstadt classroom assignments, and 2 students come up to you and say, please don't use my assignments to train your model. I'm not comfortable with sharing my personal data. So what can you really do? You either retrain the model by deleting these 2 students' data, which is super expensive, or you do something called unlearning, which is very intuitive if you really think about it. All of us know gradient descent. To learn or to minimize loss function, you do a descent in the loss landscape, and you somehow find a local minima. The basic unlearning approach is you have some document that you want to unlearn, and you do an ascent. So you do the opposite of what descent does, and you look at the gradient direction and you go in the opposite direction. And this seems to work well. There are a bunch of algorithms that people have come up with for LLMs as well. However, we recently did a paper where we show that at least at the level of language model, right now in 2025, unlearning is still not as successful as it has been advertised to be. We first show that you can recover the private information which we were talking about earlier up to almost more than 90% AURC scores or accuracy as soon as you look at the residual stream or hidden states of the model across different layers. And these are gradient ascent, NPO, RMU, all of these are state-of-the-art unlearning algorithms. Also in our work, we come up with a new sort of evaluation framework or auditing framework, where, as I mentioned earlier, if you are a startup who has to comply with GDPR law, you have to give them a report and say that this much amount of private data is still in my model, and they give you a credit score and something. So from a practical perspective, what you can do is something that we come up with in this paper, which is a mutual information decomposition framework. And this essentially gives you the amount of information, the intersection of this Venn diagram is the amount of information that an unlearning algorithm has not been able to successfully delete. Right. And finally, we make some statements for future research and we advocate for more careful evaluation for privacy in language models. Finally, do you have any questions till now? Yeah.
But how much does unlearning use the overall?
So generally these algorithms are supposed to be very successful in preserving general model capabilities. While so the question from the classroom is how much general model accuracy is preserved after doing unlearning? Yeah. So essentially people also do some tricks where you have a subset of, let's say you do some Wikipedia articles that you want to preserve, and you do gradient descent for one step and gradient ascent on the private data set. So it's a tension between what you want to forget and what you want to retain, right? And then there are more sophisticated algorithms, which I won't get into. Like SIM-NPO is like a reinforcement learning based algorithm, which is reference optimization. So you learn a reward model to understand what should I unlearn and what I should not unlearn. So you do it as an off-policy learner. And RME was again similar to a interpretability approach. You add some Gaussian noise to the residual stream. And we saw in Federico's talk as well, it just destroys model accuracy, right? So, okay. So if you don't have any more questions, I can quickly talk about some of the emerging research and open questions that if you guys are interested or if you have your own personal thoughts, if you want to pursue it, I think these are some deserving research areas that still need more attention. Like, sure, people are working on scaling up things, scaling up models, training more models. These kinds of questions I'm personally excited about. So this is an area of research in security privacy, touching on differential privacy, where can you provide formal guarantees for any language model behavior? There is some recent work, but this is super hard to do because most of the research that we do in NLP is generally very empirical and very evidential. So if you observe some outputs in the text, you say, okay, my model is performing well or not performing well. However, generally, some of you are from a mathematics background, you generally trust an algorithm if it provides you guarantees or bounds, upper bound, lower bound. So an open research question is, can we provide formal guarantees for any language model behavior, be it memorization, hallucination, and so on. The second part, I don't know if you know what homomorphic encryption is, where you assume the model has done the absolute worst, it has memorized everything, it knows it contains private data. At this point, what can you do? What you can still do is during the inference stage, during the next token prediction, you can add a homomorphic encryption or do a federated learning setup. And but this is still a very tough area to apply language models in because this does not scale at all. Like state-of-the-art research in homomorphic encryption just assumes that you are working with integers. And with language models, all of us know we have floating point weight matrices. This is very interesting. Again, this is something less than a week ago, OpenAI released ChatGPT agent, which connects with deep research. So I think as more and more people start using LLM-based agents like Cursor, GitHub Copilot, and so on, not just privacy issues, but a lot of new kinds of adversarial attacks can possibly come up, which we don't even know. So this is also an active area of research where we identify what could go wrong if you deploy like 2, 3 LLMs on your personal PC or laptop, right? And then I had, yeah. So if you have time, you can go to this website. I really like this tool. I wanted to end with this thought that whatever we've discussed in this brief talk, you assume that the model has access to your private data. However, there is a growing area of research which shows that these models are becoming so powerful that even if they don't train on the data, they can still infer a lot of personal information just based on prompt, or even if you provide a image, they can infer a lot of personal data about you. So this website is a really nice tool where, given a Reddit comment, Reddit is supposed to be anonymous. These researchers from Bulgaria essentially benchmarked a bunch of state-of-the-art LLMs to see whether a language model, just based on what I've written on a Reddit comment, can they infer my location? Can they know I'm from India or I'm living in Darmstadt and so on? And you can compete against LLMs on this website. It's like a leaderboard. It's super interesting. And spoiler, LLMs are really, really good at this. I tried to play it, I failed, but you guys should give it a try. And yeah, if you have questions, that this was the brief talk. And even after the talk, if you have any more thoughts, you want to discuss something, I'll be here. Okay. Okay.
Yeah. I don't even know why I don't even know why I'm coming here, just to say that. Now we go to the other speaker. Yeah, yeah. Okay. Floor is yours.
All right.
Okay.
Okay. Where do I click?
Actually, I should have done this before, I guess.
No worries.
Actually not. Oh, wait. Doesn't go as wide as it presents.
Maybe a left to right. That will solve the problem. Yes.
Oh no, you have a feeling.
All right. Okay. All right, cool. Thanks for everybody. This is the last talk, I think, for today. So hopefully it will be short and sweet. My name is Cecilia. I'm also a PhD student at UKP. As you probably guessed, all of us were from the same lab. So yeah, today I'll talk about my research topic, which is so when we think about culture, I don't know what comes right to your mind. Perhaps it's painting, performance art, music, literatures, memes, animes, I don't know. But all of these you're correct. They're part of culture. And in NLP, we work with all of these kind of mediums and forms. However, culture is more than just the stuff you see on the screen. For example, what I eat every day for lunch, that's actually related to my culture. So you all heard about ChatGPT is achieving superhuman performance in reasoning. It can solve PhD level math, do research. But if I just ask a very simple question, I'm not sure if you will be able to read the font, the screenshot there. Simple question. As a thousand Chinese, what dishes do I usually have for lunch? And please list 5 and don't explain. And ChatGPT returns with me with 5 different dishes. However, that if you're from, I guess, China or having an Asian background, then it's very easy to realize, oh, all these dishes are Cantonese dishes. And if you know the geography, Canton province, it's just a very small, well, not that small, but relatively small province in, I don't know, more than 10 provinces in southern China. So if I ask a little bit more specific question, as a Hainanese in China, which Hainan is that tiny little red dot, that island underneath mainland China, what dishes do I usually have for lunch? And list 5 don't explain. ChatGPT gives me another 5 different dishes. However, one interesting thing is it recommends Hainanese chicken rice as the lunch. So even though Hainanese chicken rice has the word Hainanese in it, it's actually not a really Chinese dish. It's actually Singaporean or Malaysian dish. So because ChatGPT here thought about, I guess maybe, there are keywords overlapping, so it makes sense to recommend a dish that has the same, name in there. It must be Hainanese, right? But that's not the case. And what's also interesting is that if I ask the same question, the generic Southern Chinese question in a different language, in Chinese, now it starts giving me actually very representative generic Southern Chinese dish. So that's interesting because if I asked GPT model pretty much the same question in different languages, I get different set of representations, answers from the model. And that's actually not just ChatGPT. So similarly, if we asked large language model with something that's related to Arabic culture versus like what do people actually go after, go for a drink? As you might know, that in English, like if we say we go for a drink, that's probably referring to something alcoholic. However, in Arabic culture, especially if they're Muslim religion, then drinking is not part of the conversation. Go for a drink usually refers to coffee or tea. So similarly, ChatGPT was actually trying to generate something that's more aligning with Western culture. So the question is, if we have an Arabic large language model, does this problem solve? And it turns out to be actually no. So even if we asked like an Arabic language model that's natively trained with Arabic, somehow, there's still very Western entities that commonly show up as their recommendation for drink. For example, tequila, as you see there, even though the first one, coffee, was correct or acceptable. So models are actually biased in one way or the other. And just by changing to a language does not seem to be solve essentially this biased representation issue. And, more, I think something with a little bit more consequences is, for example, this one research find from the Nature paper, where if I have basically pretty much the same message and trying to let ChatGPT to produce the essentially attributes of the person who wrote these messages. One in standard American English, one in African American English. And the model will try to rank essentially very different attributes simply based on the linguistic pattern that is inputs. Which is quite bizarre because we can actually deploy and actually, a lot of startups are actually trying to use large language models and these AI technologies to screen resumes automatically. So that means regardless, perhaps if somebody is qualified for a job or not, just because of your linguistic marker, you might not get the interview or you will not be qualified for the job. And I don't really know, this probably also, happens to different dialects. So if you know dialects, German dialect, Hessian or Bavarian, you should try this to see if there are actually different attributes, even associated with essentially different German dialects. So yeah, hopefully at this point, you kind of see the real consequences of what's going on. Because large language models have been, increasingly much more useful and becoming more agentic, meaning that they will be a lot more autonomous. They can make decisions, and probably in the future that we just give them the commands, they will go, out there to negotiate, mortgage deals for for buying a house or buying insurance or something on behalf of you. However, they lack really the cultural understanding and fair cultural representations. And they're not very usable for people who don't really speak English. And they make mistakes, and they're biased, and perhaps also will cause harm and safety concerns to people in real life. So you probably heard about the hot word called alignment research. And a very common question that people ask is that, okay, alignment, sure, that will make large models safe, and we will not get all killed by AI and etc. But really, you probably would also heard about this question: alignment with whom, right? And so we still need to make sure that these kind of research and large language model technologies should be safe for. In terms of culture perspective. And so culture is actually very multifaceted and complex. And it's, everything that we talked about in the previous slides, like memes, paintings, literature, performance arts, what dishes I eat, what language or dialects I use. And they're essentially describing group characteristics. And cultures can be, studying different aspects. They could be ideas, such as concepts, knowledge, values, norms, or even like books and artifacts. Or they can be linguistics, like the dialects examples see, or essentially how I speak or the style of writing that I, write. Or they can be social, like, for example, demographic characteristics. For example, my culture, I would believe that, will be very different from my grandma's perspective, culture in that perspective. And also context, historical context or situational context, relationships. There's some form of relationships that only exist in certain culture versus the other. And so they're very multifaceted. So then the question is, like in large language models, how do we actually evaluate them? We can see an example in communications. So many cultures have proverbs and sayings, and we use them in conversations. So like, for example, I'm planning on doing a multilingual, multicultural project. And someone can answer, well, fortune favors the brave. That is the saying. So if you learn English, and you have exposure enough to English, it's a little bit easier to actually not difficult to guess the meaning of what fortune favors braves mean here. For example, my research direction is hard but exciting. I'm going to be successful, or I'm not going to be rich because I'm not brave enough. So certainly it's probably the first answer. So we have a lot of these proverbs names that we used in conversation and communication, and we could actually use them to evaluate large language model, whether if they understand something in a contextual communication setting. And so this is basically one work that we've done to collect these proverbs and sayings used in conversations and to probe, essentially, and evaluate large language models across different various sizes. And we found that actually large language models aren't very good at understanding these contextualized cultures or common grounds used in conversation. But of course, proverbs and sayings are not just the only thing you can use for evaluating large language models. If you pay attention to research, you probably also heard like MMLU, like these kind of exams and all these common sense reasoning question benchmarks. I mean, you can also use them to evaluate large language models, and there are also cultural variations of these benchmarks. And there's a branch of research in that direction to really just evaluate the capability of large. And what I want to really focus a little bit more today to talk about is this cultural values, which is one aspect of culture. So we as humans, we all have values. And this is not really a new topic that we study in computer science. In fact, that social sciences and humanity has been studied at this for a very, very long time. And there are existing protocols and standards to actually evaluating cultural values, such as the Hofstede cultural dimensions or world value surveys. Essentially, in human, how these social scientists measure our value is they have a bunch of questionnaires, standard questionnaires, and they will go out, ask sample represented distribution of people, for example, citizens of Germany or citizens of, England, and ask everybody to answer the same set of questions, multiple people, and then compute essentially the distribution of their answers. And you can either, show the distribution of how they answer things and group the questions into different buckets, or map them into something like the cultural world value survey, the Engelhardt world culture map that's above, where that's every country are sort of have slightly different values. And if you really compare them, that's you see some interesting patterns there. So this is how we actually measure human values in social sciences and humanities. So how do you measure values in large language model? In fact, it's very easy. So we take the similar question and we just ask large languages and try to see their answers. And so that's interesting. So if we instruct large language model with a generic system prompt, you're an average human being responding to the following survey question. Large language model will give a set of answers, right? And then we can do the same thing and map them into this cultural value maps. And I'm not sure if people can see the red dots there. Those are the GPT responses. And the responses are very, very close to, I guess, the cultural values from Sweden, Norway, Finland, Switzerland, Great Britain, Canada, Australia, and New Zealand. So I guess a little bit to the north and probably a little bit to English-speaking world. And they're very on the ChatGPT are very on the self-expression side and also secular values. They're probably less religious. So, which means that, if I'm a person living in, say, Peru or from Mexico, how ChatGPT behaves and its opinion probably does not really align with what I prefer. So how do we do this? How do we actually make them to be a little bit more culturally aligned with people from different parts of the world? So one thing people find is that very simple. Well, we can ask the ChatGPT to role play a generic human being. We can also give them a little bit cultural information and let them role play somebody from a different country or different culture. So the research from this work has found that if we just tell ChatGPT to role play, for example, someone from Peru or Haiti, it will actually shift the distribution answers from ChatGPT closer to the answers from that particular, as if a human would answer those questions from that particular country. So this seems to be a good solution and simple and easy, right? Well, there is a slightly better way of prompting than just giving it a cultural information in the system prompt, which is to, give a little bit more specific instruction. For example, give its following anthropological way of thinking to actually reason when they see a question that's related to value. So to essentially prompt large language model to have a little bit more structured thoughts. And with the specific guidelines of you should think carefully before you answer the questions plus role play, large language model seems to improve their alignment to a particular culture value further. So is prompting really the solution here, right? In the sense that we've seen many research or even on the news that by change the prompts that you use to evaluate large language model, you can essentially shift, the cultural preferences, cultural value, and behavior of the large language. It sounds actually very good and easy. However, this builds on the assumption that model has already been trained with essentially the related knowledge and behavior. And the prompting, literally what it does is trying to surface what's already been learned. However, this is a very bad assumption, flawed assumption, in the sense that, number one, there are a lot of low resource culture that's basically probably never really in the training data. And then the second is that even if it's in the training data, there's no guarantee that model already learns them well. So prompting really can only solve a small part of the problem. So then we going back to perhaps training is actually the right approach. We still need data, we still need to develop better training methods so that the model can align to different values better. So one issue with this approach is that, okay, training that's good. However, if we can only evaluate values of the large language model using the survey data, the world value survey data that we've seen before, what would be the training data? What can actually change the value of models? So that's a interesting question. So it turns out, for example, our cultural value determines what we actually think it's good versus bad. So if, for example, I'm coming from a collective culture, so perhaps, I should always help my neighbors, always help my extended family, always, prioritize group interests before my own interests, versus if I'm coming from an individualistic country, then perhaps it's the opposite. And it turns out this value preferences also changes our perception of hate speech. And even with the same piece of hate speech data, research found that if you just ask different people from different English-speaking worlds of the same English data, you will get a different distribution of what people think as hate speech versus not, even though everybody speaks English. In all these countries, it's one of their official language, but people have a very different opinion. So then that's interesting. This task is essentially related to value, but it's not directly measuring value in some sense. So it's different than the survey data. So then perhaps, we could actually use survey data as the training instead of evaluation. They more or less represents the broad truth of what social scientists think is the value of a particular country, and then evaluates the trained model with these hate speech classification data. And that's this work that appears at Mirix last year, which essentially is the setup. What they've done is they take the survey data and try to do semantic augmentations, means changing essentially how the questions are phrased from the World Value Survey, and use that as training data, doing parameter efficient fine-tuning, and then evaluates the adapted model on the hate speech classification data that's it's value related. And it shows that, okay, after this kind of training and adaptation, the model seems to be, more improved in terms of their ability in doing hate speech classification. However, there is still a little bit things that's a little bit too good to be true. So if we examine the kind of questions that's being used in these social scientist surveys, right? The questions are on scale of 1 to 2, 1 meaning yes and 2 meaning no. Would you be comfortable of having heavy drinkers as a neighbor, right? Like I can say yes or no, sure. But really, the hate speech classification are quite, different. There are many, many different cases could be actually classified as hate speech. Versus that training data consists of statements and questions for something that's like this high level. It really feels like we're actually missing context, and using that to train the large language model is not contextualized. So we have I guess, and indeed that is actually true. So we have a new work that's actually showing that, using essentially survey data to train large language models and improve downstream hate speech classification tasks. The improvement isn't really coming from essentially value alignment, but coming from something else related to whether the model is instruction to versus not. So then we're going back to the square one question that, okay, so we can definitely evaluate input speech data from different cultures. And we can also use social scientist surveys to ask large language models to see whether you have certain belief or not, and use that as a measurement culture. But however, we still don't really know what training data that can change essentially models' behavior in this perspective. And in one of the recent work that we had is to have this synthetic data that we try to collect using role playing from larger models. And as I don't know if you know, but it's not hard to guess. Usually larger models are more aligned to particular culture model, even though they're still not perfect, but they're usually more aligned compared to smaller models. So we could actually use larger models to role play people from different cultures using a more contextual planning to generate these social interaction data and train large language. And it turns out these social interactions seems to be actually what's actually quite helpful in terms of value alignment in the large language models. So yeah, so I think we talked. The volume is a little bit strange. Okay, anyways, so we talked about a lot of things that's more foundational with large language model and safety values and evaluation and all that stuff. So I want to just take a little bit of time talking about the real world application. The foundation model research is a little bit too far from real. So it turns out it's also not just value or safety or anything, like people's distress is also actually culturally related, and how we actually perceive emotion and how we actually feel motivated by emotion and what are the emotion stressors are also cultural specific. So that's clinical psychologists has had a long history of doing this cultural sensitive emotional support, which we could also do this to actually change this to make large language model more culturally aware in terms of sports specific guidelines. So yeah. So with that, hopefully it's not too boring. That's large language model will change essentially everyone's lives. And for this change to be positive, it really requires essentially large language models to have cultural understanding and alignment to values for pretty much. And large language models are far from being, able to achieve that. And there's much more research to be done in this area. And thank you very much for your attention. Questions? All clear? All good? Problem solved? Good.
Yeah. Okay. I have the experience with a lack of questions, by the way. I had to repeat 20 times per lecture if there's any doubt until someone tells me. Yeah, until someone tells me if I can go back to the first lecture 2 months ago because they understand what a neural network is. Okay, so I guess this is the end. So thank you everyone for coming. I guess what I wanted to show you is what is kind of done at TU Darmstadt here. Of course, it's just a couple of the topics that are covered, but we couldn't have 20 hours of invited talks because the UKP lab is actually quite big. But also what I wanted to show you is that there's really a huge spectrum across which you can go when you do research, whether it is inspecting the effects of prompting on LLM. So if you want to really go deep into the technical aspect and crack it open, the transformer attention head or whatever, to understand what is happening inside there. So I guess we can conclude now. If you have any private question, we were shy, you can approach the speakers after we just conclude. They don't bite usually. And yeah, thank you everyone. And gentle reminder that next week there is a exam mock-up simulation. You can come, you cannot come, will be put on Moodle. Okay, so thank you. Have a nice day.